All right, let's jump right in. We're going to tackle one of those questions that sounds like it belongs in a philosophy class, but trust me, we're going to solve it with straight up science. It's one of those classic thought experiments, the kind that really makes you question what's even possible. So here's the big question for you. Can you actually track a single drop of water in the ocean? I mean, really think about it. At first glance, it might sound simple, right? But the universe has some very, very strict rules. And those rules are about to make this seemingly simple problem, well, a whole lot more interesting. Okay, so here's our game plan. We'll start with the physics no, why this whole idea seems totally impossible. Then we'll hit an engineering pivot, look at 3 awesome chemical solutions, tackle some of those gotchas you're probably already thinking of, and wrap up with what this all tells us about the scientist's mindset.
All right, section 1, the physics no. Before we can even get to the clever solutions, we first have to understand why this problem is so incredibly hard. And if you ask a physicist, well, from a pure physics standpoint, the answer is a hard, definite no. Let's dig into why that is.
So the very first roadblock we hit is something called quantum indistinguishability. It's a fancy term for a simple, kind of mind-blowing idea. Every single water molecule is a perfect, identical twin of every other water molecule. They don't have little serial numbers stamped on them, It's not like a factory line. One H2O is an exact clone of the billions and billions of others. There's just no way to tell them apart.
And if that wasn't enough, there's another massive force working against us: entropy. Think of entropy as the universe's unstoppable march towards chaos and disorder. The second our little drop of water hits the ocean, bam, entropy gets to work, just scattering those molecules everywhere until they're totally, hopelessly, randomly mixed in.
So you put those two things together, molecules you can't tell apart and a universal force that wants to scatter everything, and, well, physics gives us its final answer. That little group of molecules we called our drop, it's gone. Poof. It doesn't just get lost in the crowd. For all intents and purposes, it literally ceases to exist as a thing.
Okay, so physics basically tells us no way can't be done. It lays down the law. But this is where things get really cool. This is where we stop thinking like physicists who just observe the rules and start thinking like engineers who ask, how can we change the rules of the game? And that leads us to the big pivot, the game-changing question. What if we're allowed to modify the drop before we put it in? I mean, if the whole problem is that we can't tell our water molecules apart from all the other ones, why don't we just make them different? And just like that, with one simple change in perspective, an impossible physics problem becomes a totally solvable engineering challenge. And that engineering pivot, it throws the door wide open for chemistry to come in and save the day. In fact, chemistry gives us not 1, not 2, but 3 completely different ways to solve this. We're going to break down these 3 chemical solutions right now. All right, solution A, this one comes from the world of physical chemistry using isotopes. And the core idea here is actually pretty simple. What if we just change the weight of our water molecules? We're going to make our drop literally heavier than any other drop in the ocean. So how do we do that? Well, we take the regular hydrogen atoms in our water and we swap them out for their heavier cousin, deuterium. It's what's known as an isotope. This creates something called heavy water. Now, here's the nuance. Entropy is still going to do its thing. Those molecules are absolutely going to get scattered all over the place. So we're not going to find our drop all neatly together. But, and this is the key, we can now find the original atoms of our drop because they're heavier than everything else. We can track the pieces, even if we lose the shape. Okay, that's one way. But what if you're thinking, no, I want to find the drop as a drop. I want to keep it together. Well, for that, we need a different toolkit. Let's move on to solution B, organic chemistry, and a little trick we can borrow from biology. The concept here is encapsulation. We're essentially going to build a tiny little bubble around our drop of water. We'd use something called a lipid bilayer, which is just a fancy way of saying a shell made of fat molecules. It's the exact same stuff that makes up the walls of the cells in your own body. Since these lipids are carbon-based, it's a perfect organic chemistry solution. It's like putting our drop of water in a tiny, microscopic raincoat, keeping it safe and separate from all the other water. And that brings us to solution C, our most high-tech option yet. This one comes to us from inorganic chemistry. So we're not going to change the water's weight, and we're not going to put it in a container. Instead, we're going to tag it from the inside with magnets. Here's how it works. We'd suspend teeny tiny magnetic nanoparticles inside the drop itself. We're talking about things like iron oxide, which is basically just microscopic rust. And since iron oxide is a metal, not carbon-based, this is our inorganic solution. The result? Our drop of water is now magnetic. We could, in theory, track it from a distance just by looking for its magnetic signature. Pretty cool, right?
So let's just quickly pull all that together. Look at this. We've got heavy water from physical chemistry to track the molecules by mass, even though the shape is lost. We have the lipid bilayer from organic chemistry to encapsulate the drop and keep it distinct. And we have nanoparticles from inorganic chemistry to tag the drop with magnets for remote tracking. We went from absolutely no way to having 3 completely different, totally viable solutions.
Okay. I can practically hear some of you out there going, hang on a second, right? There are a couple of big gotchas here that we need to talk about. So let's just dive right in and answer them.
All right, gotcha number 1, the big one. But the ocean is huge. It's unbelievably massive. You're right. The concentration of our tagged molecules would be so incredibly tiny, it's hard to even imagine. So how on earth could we ever actually find them? And look, that is a fantastic and very practical point. But it's important to remember what kind of question we're asking. This is a thought experiment about what is possible, not necessarily what is practical with today's tech. So yeah, finding them would be a ridiculously hard detection problem. But are the tagged molecules still there? Yes, they exist. The problem is one of detection, not existence. So in theory, the answer is still yes. Okay, gotcha number 2. This one's a little more philosophical. It's about the encapsulation idea. If you put a shell around the drop, have you cheated? I mean, is it really still a drop of water in the ocean if it's not actually mixing with the ocean? I absolutely love this answer because it's so elegant. The way to think about it is this. It's just a drop of water wearing a raincoat. That's it. The stuff on the inside, it's still 100% water. We haven't changed the drop itself at all. We've just given it a little coat to stop it from mixing. So yep, it is still a drop. So let's take a step back and look at the big picture here, because this whole thing, this journey from impossible to possible, isn't just a fun little puzzle. It's actually a perfect window into the scientist's mindset. It's all about that critical shift from asking why not to asking how to. This is really how scientists solve problems every single day. First, physics comes in and tells you the fundamental limits. These are the unbreakable rules of the universe. Then, engineering gives you the creative pivot, that moment where you reframe the question to find a way around the rule. And finally, chemistry swoops in with the specific, practical tools to actually get the job done. That interplay between disciplines, that's where all the magic happens. That's the engine of innovation. And that's really the big takeaway, isn't it? That blueprint for solving the impossible is right there. You understand the fundamental limits, you find a clever way to reframe the problem, and then you apply the right tools. So, I'll leave you with this question. What's an impossible problem in your world that's maybe just waiting for the right pivot? Something to think about. Thanks so much for diving in with me on this one.